Welcome to this explainer. You know, right now, deep beneath the surface of our oceans, there is this massive, entirely unseen shift taking place. We're talking about a fundamental change to the planet's operating system. It's a shift so huge, it literally redraws the map of our future climate. But before we even get into the hard numbers, I want you to just think about something for a second. What if our climate models, the actual tools we rely on to predict and prepare for the future, what if they were missing a crucial blind spot? Well, a brand new, honestly groundbreaking study published by researchers at CNRS INSU suggests that's exactly what's happening. They've uncovered this hidden variable that kind of changes everything we thought we knew about how our oceans are reacting to a warming world. Okay, let's dive into this. When you look at those deep reds and vibrant oranges surging upward, you're seeing vast amounts of warm water moving northward. It is, quite literally, a planetary engine, and it's doing the heavy lifting of keeping our global climate in check. Scientists call this engine the AMOC, that stands for the Atlantic Meridional Overturning Circulation. Think of it like a giant global conveyor belt. It's this crucial ocean current system that transports heat from the warm tropics all the way out to the North Atlantic, and it's moving millions of cubic meters of water every single second. Just to put that into perspective, that's actually more than 100 times the flow of the entire Amazon River. Without the AMOC constantly turning away, the temperate, stable climate that places like Europe currently enjoy, it simply wouldn't exist. It's an absolute powerhouse for regulating our global climate. Now, what's really interesting about this is how much our understanding has just shifted. For years, the old consensus among climate models was that under an intermediate emission scenario, the AMOC would slow down by about 32% by the end of the century. But honestly, those estimates were always clouded by a pretty high degree of uncertainty. The new reality, which was just brought to light by this latest study, calculates a massive 51% slowdown by the year 2100. To really wrap our heads around the sheer scale of this discovery, we have to look at the relative difference. 60%. This newly revised 51% drop is actually a staggering 60% more severe than what previous climate models averaged out to be. So we aren't just talking about a minor statistical adjustment here, right? We're looking at a fundamentally steeper, much more drastic decline in our ocean's ability to circulate heat across the globe. So how exactly did researchers uncover this massive discrepancy? How did they manage to cut through the noise and drastically reduce the uncertainty that was plaguing all those older models? Well, it really comes down to some incredible scientific detective work. They knew the old models were diverging wildly from one another, so they set out to find the missing variable. They were looking for that one specific data point that would finally bring our future into clear focus. To do this, the team actually applied 4 different methods to constrain the climate models using real-world observations. But they really hit the jackpot when they used an advanced statistical tool called regularized linear regression, which I know sounds like a mouthful, but it's essentially just a brilliant mathematical way of untangling massive, super complex webs of data to find the absolute strongest connections. By feeding this model a literal mountain of real observed variables like actual temperatures and actual salinity levels, they were able to pinpoint exactly where those older climate models were drifting off course. And that brings us to the hidden clue that cracked the whole case wide open. The researchers noted that their dramatic new projection comes directly from, and I'll quote them here, the correction of a bias present in the models concerning the surface salinity in the South Atlantic. It turns out the saltiness of the water right at the surface of the South Atlantic was acting as this massive blind spot. The older models were miscalculating it, and that single bias basically threw off the entire global projection. Now, you might be sitting there wondering, why does salt matter so much? Actually, it's just simple physics. Saltier water is denser, right? It's heavier. So it acts like this giant weight that drives the sinking motion powering the whole ocean conveyor belt. If the salinity is miscalculated, the stability of that entire engine is totally misjudged. And recent work shows this specific South Atlantic region is deeply linked to the existence of a potential tipping point in our entire global ocean system. So the absolutely crucial point here is, what does all this actually mean for us? It's incredibly easy to get lost in the weeds of abstract oceanography and advanced statistics, but we really need to cross over into the tangible, real-world stakes. Because an ocean engine operating at just half capacity, that isn't just some interesting scientific footnote. It's a profound world-altering event that will dictate the future of our environment. Let's break down the harsh realities of a 51% slowdown. Because a weakened AMOC is going to drastically disrupt life as we know it, both regionally and globally. First off, we're looking at severe changes to European temperatures. Without that massive influx of warm water, Regions that usually enjoy mild winters could suddenly face deep, destabilizing freezes. Second, this disruption rewires global precipitation regimes. It alters exactly where and when rain falls, which, as you can imagine, throws agriculture and freshwater access into absolute chaos. And finally, compounding all of that, an altered current actually accelerates the rise of our global sea levels, threatening coastlines all over the world. Okay, I know that sounds heavy, but despite these severe projections, there is a silver lining here, and that is the power of accurate data. By finally quantifying this risk with significantly less uncertainty, these scientists have given us a massive head start. They've provided the exact, precise estimations we desperately need to improve our global adaptation strategies. Because, let's face it, we can't prepare for a problem if we don't know its true scale. But now we actually have the clarity to anticipate these impacts far more effectively. So, let's move to our final thought. The data is clear, the old biases have been corrected, and the stark reality is that our planet's oceanic conveyor belt is losing momentum much, much faster than the consensus believed. So I want to leave you with this to think about. With the ocean's engine slowing down faster than we ever anticipated, how quickly can we adapt our global strategies to survive the ripple effects? Thank you so much for joining me to unpack this essential research for this explainer. Keep learning, keep questioning, and I'll catch you next time.